I have an announcement to make. Probably, the next week we will be having a class test. That would be a unified class test for section 1 and section 2. The date and the actual syllabus will be actually announced in the Google Classroom, but tentatively, till today's class, probably till lecture 5, something like this. That your another teacher for another section is probably Tashfin Mohammed. We talked, together. So probably we'll be taking, like online assessment, together probably. I'm not sure yet, but this is what we talked, last time.
Sir, you wanted to actually know what we do want, actually, classwork or assignment. Most of the students actually went for their assignments actually.
Assignment, but the thing is that he said we need to take the the class test first. Okay, for our for my actually class section means section 2, right? This is section 2
Yes, sir.
probably. I'll be providing some assignment in case any one of you actually are not getting good marks in in the class test. I will definitely consider assignment.
So what is going to be the time frame of the class assessment actually? What
Oh,
time? What?
that I have not actually finalized. Yesterday I got an message from him, and I said I will discuss further. But he said I should have actually announced earlier, or I should announce today. That's why I'm just announcing. All right.
Okay, sir.
Yeah.
Sir, up to lecture 5 from 1.
Up to lecture 5. Yeah. He said up to lecture 6, but I have not covered lecture 6 yet. So something
Okay,
like
sir.
this.
So when will the quiz will be held?
Probably next around Wednesday. The next Wednesday.
Next Wednesday. Okay, sir.
Wednesday around 4 to 5, I think 4 to 5 or 4:30 actually PM. I'm not sure. I will definitely announce it just in a tentative announcement so that you can actually take preparation beforehand. Means you can actually read, and still if you are having actually any problem, we'll be having another 2 classes right next week. Then we can discuss what are the things you didn't understand or I need to clarify more. All right, then we can actually start our session. Let me present my entire screen.
Sir, I
Yeah, sure.
didn't get the recording of the last class. I mean, sir,
Did you check in the Google Classroom now? I have posted, I think, 10 to 15 minutes back. I forgot actually. I thought, I have
Oh,
posted.
okay, sir.
Yeah. So, can you, am I audible, and can you actually see my
Yes, sir.
PDF file? Thank you so much. The thing is, the last week we had been discussing about the phasor diagram and how to actually solve SS circuit easily with the help of actually such phasor actually representation. So far, we had been actually dealing with very simple circuit. Even today, we'll be actually solving a very simple circuit for your reference. One of them is let's say we have a capacitive network. This is the network. It's look like means it's connected to some voltage source that is called VC. So one capacitor is connected to a voltage source, and the voltage source is given by a sinusoidal. So that is given by 15 sine omega t, and the reactance of the capacitive actually capacitor is 2 ohm. 2 ohm is reactance. Xc means reactance. So we'll convert it to impedance first, and then my target is to calculate the current. Look, the current in terms of actually sinusoidal, right, is a time dependent current. Means finally we'll be actually converting the current into the sinusoidal, and the another thing, so we'll be drawing the phasor diagram, as well as it will be drawing the VC and IC, like how what we have learned in the first 2 classes, like is it lagging or leading or something like this. So in order to do so, first what we got is VC, this one, like the input actually voltage. So I must actually convert it to phasor because we'll be dealing with phasor. This is the easiest thing to do. So if you recall, the last class, this is the peak value. So I need to convert it to the RMS value. So RMS value would be nothing but the peak value divided by √2. And what is the phase angle here? Plus 0 degree. So the phase angle is actually 0 degree here. Now for the capacitor, if you check here, the reactance is XC, but the impedance for capacitor, if you recall from the last class, it was like minus j XC, right? Or minus j times 1 upon omega c. So minus j means nothing but the negative 90 degrees. So we can actually write down like this. If this one is the case, what is the actually voltage across that capacitor? Is nothing but the VC, right? So what is the current actually flowing through that capacitor? Is we need to just apply the Ohm's law. Just give me a second. Hey. Hello. ওরা আশেপাশে যান না, এদিকে সরে আসুন। একটু ফ্যানটা ছেড়ে দেন না, অল্প করে। Can you hear me now? Sorry for the interruption. So if I want to actually calculate the current passing through the capacitor,
Yes, sir.
it's so simple, right? It's so simple. Like, do you agree with this statement? Like the voltage is equal to the current times actually the impedance. Do I need to explain this? Like, how did I get VC equal to IC plus
No, sir. No, sir.
No, so you explained it in the last class.
Yeah, and this is so simple, right? This is nothing but the Ohm's law, and we are replacing R by ZC and nothing else. So all you have to do, I need to find the current. So current means this, but only thing you need to consider, these are vector quantity. These are the complex number. These are the complex number, means we cannot just take the magnitude, or we cannot just consider the phase, but we must actually go for both. So if I do so, you can see we got some expression, but can you tell me, is this current the maximum current, sorry, peak current, or is it peak current or RMS current? No. Is
Sir,
this
RMS, sir. RMS.
RMS current.
Perfect. So if this one is the case, if I want to actually express in terms of actually sinusoidal, then I must to convert it to peak current, right? So what is the peak current? This value times √2. This value times √2 will be the peak current, right? Peak value. So I will put in a peak value, then sine omega t. What is that angle? Is plus 90 degrees. So I will put in a plus 90 degrees. Is there any confusion so far? Probably not. If not, this is the phasor diagram. This is the phasor diagram, and this is the normal waveform. So what are the difference between these two? The phasor diagram actually represents how does it look like? Like, means the voltage and the current relation. So if you recall this one, this is the real axis, and this is the imaginary axis. So just write down the voltage and current actually expression in terms of actually phasor. So in that phasor, you see the angle is 0 degree. So angle is 0 degree means it is on plus x-axis, and this is 90 degree. This is like this is 90 degree, then 180 degree, then 270 degree, and then again the 360 degree, something like this. But so for the VC, what is that value? Forget about value. Check the angle. So 0 degree means it will be lying on the x-axis or the real axis. So in that direction, and the magnitude would be 10. So let's say this is 10. This is 10. Let's say this is 10 point actually 605. So similarly, for the current, angle is 90 degree. You see the angle is plus 90 degrees. So I will go in the anti-clockwise. So if I go anti-clockwise 90 degree, it actually reaches here, and 5.303 would be almost half of the the size we consider here. So it would be something like this. So this is the IC. Any confusion so far here? This is so simple, and we have done this sort of waveform many times. I'm not actually explaining it anymore. you will just plot this one, like the one is, the first one is nothing but the sinusoidal starting from 0, and the second one is 90-degree phase shift plus, so it will actually start from here. So this is 90 degree. So can you tell me, is I is leading or lagging? Is I leading or lagging here?
I is leading.
I is leading, sir.
Perfect. So for the phasor diagram, I is leading means it would be on the left side, means in anti-clockwise side. If I was lagging, it would be on the other side, right? On this side, so it would be on the clockwise direction. Means angle would be different. So now we have learned what are the impedance of the resistor, capacitor, and the inductor. Now we are in a position to apply whatever we have learned from the DC actually circuit actually classes, or the theories. So one of them is like the series configuration. If you recall, from the DC circuit, EEE 101, probably the course name, we have seen, if we have multiple actually resistors of in series, then the total resistor should be given by the summation of all resistors, right? So we all know this actually formula from the series connection. Do I need to explain this one?
No,
Probably
sir.
not.
No, sir.
Perfect. Thank you so much. Now, in AC circuit, since it actually involves, the complex number, means there is a phase as well as the magnitude, that may actually create the problem. As I said earlier, if I consider is at sinusoidal, like sine or cosine term, this trigonometric actually calculations are really messy. So in order to actually mitigate that issue, what we do, we convert everything into impedance, or sometimes we call it actually impedance diagram. Means every AC component will be replaced by an impedance, equivalent impedance term. Means if it is a resistor, we'll actually convert that resistor to equivalent impedance term, means R angle 0 degree. If it is a capacitor, we'll be replacing it by minus j times xc, right? Or 1 upon omega c, whatever you actually have, you can choose. And for the inductor is similarly j omega l. So then we'll see we can actually draw the similar like things. Instead of actually drawing resistance, we'll be actually drawing a box that represented by the z. It could be R, it could be C, it could be L, it could be anything. So now if I have something like this, we can say this impedance, and this impedance are in series. So if I have n number of actually impedance are in series, then the total impedance should be nothing but the summation of all impedance. Any confusion here? No, right?
No, sir.
No, perfect. So if it is the case, I can actually solve other things really fast. Like we have learned the Kirchhoff's actually voltage law, or the KVL. What does actually KVL suggest? The total summation of all voltages in a closed loop should be 0, right? Should be 0.
Yes, sir.
And then sometimes other people say, oh, summation of voltage rise equal to summation of voltage drop. Whatever you say, both are correct. So for this case, let's say this is a circuit, is a simple circuit. There is a ground here. So previously we have solved this sort of actually like circuit many times, but now we are replacing everything with respect to the impedance. So let's say Z1 is the impedance and Z2 another impedance in that actually closed circuit, but Z1 can be anything. Z1 can be resistor, Z1 can be capacitor, Z1 can be resistor, capacitor, inductor together, or anything. But Z1 in simple term, it's a complex number, means it has a magnitude and it has a like angle. So why did I say it could be resistor or capacitor, or even the combination of that? Even if I have a resistor and capacitor in series or parallel or whatever, I can always express it into a equivalent actually complex number. So that is the case. If this one is the case, what would be the actually KVL here? Like if I use this loop, means the current is actually passing through like this. So current is actually entering through the impedance Z. So means this current times that impedance. So basically this voltage is equal to this voltage plus this voltage, right? But we can we write like this KVL, can we write like this? It's entering through the negative terminal of the voltage source, so I will write down E. Then it passes through Z1, so plus I times Z1. This all are actually vector. So it also passes through Z2, so I times Z2, that equal to 0. Is there any confusion? Or I'm using different notation?
No, sir.
No, perfect, right? So this is the case. If I can write down the KVL here or the KCL here, depending on whether we are considering actually a closed loop circuit or the parallel circuit. So if I can write like this, we can find any actually properties. Let's say this voltage is given, this impedance is given, and I'm asked to actually calculate current. So using this actually formula, we can calculate current, right? Or what is the voltage difference like between that Z2? We can calculate anything, whatever quantity they say, the power and everything. So this is a very basic and basic thing of the Kirchhoff voltage law, and whatever we have learned in the DC circuit will be applicable here too. So another thing, although I never use actually these rules, but I must actually teach you first. But I suggest always go for whatever it says, like normal KVL or KCL. Then you don't need to actually remember it every time. So there is another actually rule is called voltage division rule, right? Or the voltage divider rule.
Yes, sir.
So this is nothing but if you have a series circuit and energized by a single actually voltage source, then we can actually explicitly calculate the voltage difference across each components by writing in this formula. And what is that formula? Look, this is a series circuit. So voltage division rule is applicable for a series circuit, means these components have to be connected in series. Let's say for our case is Z1 and Z2, these are in series. Then the voltage across Z1 should be given by the impedance of that component, means Z1, divided by the total sum. This is called the total sum of Z. So total sum of Z, this is the sum, means if I have three actually elements, Z1, Z2, Z3, so in denominator we would be writing Z1 plus Z2 plus Z3 and so on, and times the total voltage, means the main actually source voltage, for our case actually E. Similarly for the voltage across actually Z2 would be will replace Z1 by Z2, because now we are considering actually Z2 element, and divided by, again, this is nothing but the sum of all Z in series, So can you tell me, if I have actually 4 components in series like Z1, Z2, Z3, Z4, what would be the expression for V4? Do I need to
Sir, at first,
Z4
Z4 divided by
Z1
Z4
plus Z2 plus Z3 plus
Z3 plus Z4 into E.
Perfect. So
And
do I
all
need
of
to
them
write?
should be in phasor format.
Yes, perfect. That is the important thing. Otherwise, it will not work. Do you understand what I said?
Yes, sir.
Yes. Okay. So that is the the voltage division rule. Sometimes you can use voltage division rule. Otherwise, just use the normal KVL to get whatever they ask you to actually solve. So now we are in a position to actually apply our knowledge into the real circuit, like some example practice problem. So in order to actually do so, just think about this circuit. In this circuit, we have a current source. It's a AC current source, as well as we have a resistor of 6 ohm and a capacitor with actually reactance 8 ohm. So what is the first step we will do? Although it is not actually shown here, the first step is whatever they ask you to calculate, draw the impedance actually diagram. Draw the impedance diagram. So this is I. What is the resistor? Write down ZR. The capacitor impedance diagram is ZC, and then you will actually do like this. Okay, so this is the actually equivalent impedance diagram. So now check what is given and what I am asked to actually calculate. So check here. This is a current. This is a time dependent actually current source, and this is a phase difference. Is it a peak value or RMS value? Tell me.
Peak
I-
value.
Peak values.
But our first task is to convert everything into phasor, right? This current
Yes, sir.
has to be in phasor. So what is the phasor representation of this one? 7.07 divided by √2.
Root 2.
Can you tell me what would be the angle?
So it should be 1. Not the angle says 707 degree. Something like that.
Oh, it should be 707, right?
Sorry, sir. Please continue. Actually, I was saying what would happen.
Okay. So angle is this, right? 53.13 degrees. So this is the phasor representation of the current is given. So can you tell me what would be the phasor representation of ZR?
Sir, 6 0 yes.
Perfect. What is the phase angle of ZC?
Sir, 8 minus 90 degrees.
Perfect. Thank you so much. So if I know the current means in this circuit now I know I know ZR and I know ZC. So the first question says number A says what is the total impedance? Now tell me ZR and ZC are they in series or in a parallel?
Series.
And series, sir.
So what is the total impedance? Just add up these two, right? So
Yes, sir.
ZR ZC, right? So can I actually replace this value like we got like this? So use your calculator. Do you know how to actually perform the complex actually addition, subtraction, and some other things? Or I need to teach that too?
No, sir. No, sir.
Though I don't have a calculator, so I can't actually do it in ES 100 ms or something series. I don't know, but you can go to complex mode and actually perform this calculation. But make sure you choose the phasor actually format like r comma theta. So if you actually use this format, you will get directly. The answer would be shown in this format first. Then if you actually go to Cartesian actually format, then this term will be shown. If you are having any issue with dealing with this complex number in calculator, either you can actually like watch some YouTube video, like it will be easier. And still, if you are persisting with the problem, you may ask me. I will borrow some calculator from someone just to show this one, inshallah. So is there any confusion? This is the total actually impedance. If
No, sir.
not,
No problem.
no problem at all. Can we actually draw the impedance diagram? Oh, what does it mean by impedance diagram? Impedance diagram is nothing but the phasor diagram. So impedance diagram is nothing but the phasor diagram, but we will plot all the impedance separately. Means for our case we got r theta, right? Two impedance ZR and ZC. So we'll be plotting ZR and ZC. So what is the expression for ZR? ZR was 6
Sir, 0 degree.
0 degree, right? 0 degree means it should be lie on. This is the real axis.
X-axis.
Yes,
This
sir.
is the imaginary axis. So it will be lying on the x-axis, right? So this is 6.
Yes, sir.
And the second thing is ZC. What is ZC? Like ZC was 8
Sir,
negative 90 degree.
Negative 90 degree.
So negative
Yes, sir.
90 degree means it's clockwise, right? Clockwise
Yes, sir.
90 degree. So this is actually basically negative 90 degree. It's negative 90 degree. So I have drawn 8 here. Now, what is the total impedance? What is the total impedance we got? 10, right? So
Yes,
you
sir.
check what is the angle? Negative 53.13. So negative 53.13 is this, and this one would be 10. And interestingly, you will see that this 10 we got in that format. You see, this is nothing but a right angle triangle. So right angle triangle, and this is the hypotenuse. So hypotenuse is equal to what? This term is nothing but the root over r square plus xc square. So this is xc and this is r. So and this is the hypotenuse. So formula for hypotenuse is equal to root over the base square plus the what is it called, like opposite square. So you'll get this value. Am I clear? Or am I teaching a bit fast today?
No, sir. No problem.
No problem at all, right? Thank you so much. How about other student? Why don't they actually interact? You can interact in my class, nothing will happen, inshallah. So the other thing is, the second part is I need to calculate what is the voltage across the resistor as well as voltage across actually capacitor. But check, this T means I need to express the final results in actually sinusoidal form. And I also need to calculate what is the total voltage, means the summation of VR and VC. Let's check it out. What is VR? What is VR? I times R, right? What is VR? The
Yes,
current
sir.
times R. And what is VC?
Yeah.
The impedance of VC
Impedance of the
capacitor
capacitor
times
into current.
current, right? So it's
Yes,
so
sir.
simple. Like, check
Yes,
it
sir.
out. So we have done it previously. We have converted every actually thing into phasor. So VR equal to nothing. Current passing through the resistor times the impedance of resistor. So we'll get some value. VC is nothing. Again current passing through the capacitor times the impedance of actual capacitor. You get some value. So total voltage would be nothing. Just the summation of these two. So you'll use the summation of these two. Now, since everything should be written in terms of actually time domain or the sinusoidal form, these are the actually what value? These are the RMS value, right?
Yes,
So
sir.
for the peak value, what we will do
Multiply with
with
root 2, sir.
2. So if you multiply with root 2 means this one times root 2, that will actually provide you this, and so on for the other things. Similarly, if I ask you to calculate the phasor diagram, then that should be so easy. This is a real axis, this is the real axis, this is the imaginary axis, and you will be drawing all components separately. Means VR, what is the VR? 42 point something with angle plus 53.13. So plus 53.13 means upward direction, and you will be drawing that line. And similarly, VC equal to minus 36.86. So minus 36.86 means something like this, and the magnitude is 70, something like this is that. And finally the total voltage is nothing but the 70.70, and there is no angle. That means it will be lying on the real axis. Is there any confusion here?
No, sir.
No, sir.
No? Perfect. So now this is the same thing. Instead of having a like resistor and capacitor, we are dealing with RLC circuit. Who was taking actually like EEE 204 lab course with me? Like there are a few students who have done the online lab session yesterday, right?
Yes, sir. Sir, I was doing the
Okay.
lab
So
course.
yesterday we had done some series resonance or something, right? The resonance things.
Yes, sir.
Yes, something like this. So this is that circuit. Like we have a RLC. So a resistor, then capacitor, and the inductor, and the voltage is given. So first we need to convert that E into phasor. So 70.7 divided by root 2. What is the angle? 0 degree. So can we actually draw the impedance like diagram for this? Means what is with the Z here? 30 degree. What is the XL? 790 degree.
Plus 9.
What is the XC?
Plus 90.
Three?
Three negative
90.
90.
So if I know, I will not do this one. Check it out. What is the total impedance? Tell me, ZR, Z. Now there is no RLC. This is ZR, this is ZL, and this is ZC. Now tell me, ZR, ZL, and ZC, are these in series or parallel?
So in series.
In series, perfect. What is the total impedance? Just sum it up.
Yes, sir. It will be.
No problem. You can just do the calculation, right?
Yes, sir. 5, and angle will be, sir, 53.13 degree.
That's perfect.
Yes.
53.13 degree, something like this. And you can draw, the impedance diagram. So this is nothing but the impedance diagram. Can you read my, handwriting, or is it like, the messy, doctor handwriting?
No problem.
Like you
sir.
can never actually
No, sir.
read.
It's
All
all
right.
right.
Thank you. At least you can actually read. That should be fine. So the second thing is that I need to find what is the current flowing through the circuit. Since it's a series circuit, we will get a single current. So what would be that current? what would be that current? I can apply the KVL, right?
Yes, sir. KVL or Ohm's law.
So yeah, anything
same
you
thing.
can actually go for.
Yes, sir.
So can you tell me what would be the formula here? Can I write down like this? Negative E plus I times R means not I times ZR plus I times ZL plus
sir.
I times
Times
ZC
ZC equal to 0.
0, right?
Yes, sir.
So if I use this is loop and this is current I. So from here, can I actually calculate I? Means I equal to E
Yes,
divided by ZR plus ZL plus ZC, right?
Yes, sir.
So you'll
Yes, sir.
just use this formula. And sometimes people do like this. Oh, find the total impedance and then current equal to E divided by total impedance. That is another way to do so.
Yes, sir.
What is Z? VR, VL, and VC. VR means this I times ZR. VL means I times ZL. VC means I times actually ZC. Any problem with that? Means still here. I'll not actually
no.
write this. Although
problem.
the workout is here, you can check, but I'll not do that because this is quite simple. But I'll do this two part. Like I need to calculate what is the total delivered to the circuit. So now my target is to calculate what is the total delivered to the circuit, and the second thing is the total power factor, overall power factor of this like circuit. So now first I will talk about the power delivered. Power delivered. What do you mean by delivering power? What do you mean by delivering power?
The component is absorbing power.
Yes, perfect. So power, if you remember correctly, the total power of an AC circuit is the source voltage times source current, means the main current, and cosine of the difference between these two actually
Voltage and current angle.
Yes, we have learned this, right? Like P equal to, we learned this formula, P equal to VI then cos theta, right? But remember, these are always RMS value. Or if you wanna use the peak value, there was another
Sir,
formula.
is it the average power?
Yes, this is called average power. This is called average power. So there was another formula, and these are the peak value. So whatever you like, you can actually choose. So I suggest to use VI cos theta. This is the easiest actually thing to do. So, and theta means nothing, the difference between the voltage, actually angle of voltage and angle of the current. So from that actually relation, from that actually circuit, this is the circuit, we already know what is the expression of E, means this voltage, and from the second number B we can calculate I. So I know I equal to some value and then angle. So once I know what is the actually voltage, input voltage and input current, we can easily plug this here, right? V and I, and we can get some results like this. This is the E and this is the I. So I will just plug this value. Theta V means 0 degree, theta I means this, theta V means 0 degree, and theta I means negative 53.13 degree. So if I do so, then I will just plug this actually value here, and you will get some certain actually total value, and that is called the total power. Now what is called power factor? So power factor means
Cos theta V minus
yes,
theta I.
perfect. So if this is the case, nothing, whatever value is here is the power factor. So theta V minus theta I, you will be writing down. But as I told you, you actually in the probably the last class, we must mention, or last class, we must mention that power factor is it leading or lagging or what? So how do we actually define the power factor is leading or lagging? Because
If theta V
theta
if theta V minus theta I is
Negative?
positive, then
lagging.
it's positive, then V is leading, or else is lagging.
Okay, you can check from two things. Like just think from here. Can you tell me, is current is leading or lagging?
So current is lagging.
So current is lagging means power factor is lagging.
Power factor is lagging as well.
If current is actually leading, then power factor is leading. Okay.
Yes, sir.
Any confusion, so far?
No, sir.
No? Are we good? Till here?
Yes, sir.
Let me actually save that one. How many students are here? 12 students are here. I have actually announced, something in the beginning of the class. So whoever have missed, the first actually few minutes of our, today's class, we might have actually a online quiz on next actually Wednesday. If it is confirmed, I will actually definitely like announce it in Google Classroom, and the syllabus should be up to lecture 5 probably, or some part of lecture 6, but I will try not to actually include lecture 6 for the first actually class test, and as well as I will be taking some assignment for your actually convenience. Like if anybody actually didn't do well in that the online the like tests, I'll consider probably that assignment also. Any question so far around about the class test, anything? Let me actually give you some hint about the class test. You must to go through all the class lecture we have actually discussed in our live session, but what I suggest, try to understand the basic. So if you understand the basic, you can answer the question within a few minutes. If you don't understand the question, even if you have 2 hours or 3 hours, you cannot answer the question, or you cannot solve the problem. So the question would be really simple, but you must use your brain. Like it would not be that simple, like you will go and write down the answer. So I will just test how much did you understand the like topic or the idea, nothing else. So this one is a case. Let's get back to the next actually lecture. This is also very simple. So in the last actually section, we had discussed about the series circuit, like how to calculate total impedance or total current or the voltage across certain actually circuit parameter. But now we'll be dealing with parallel AC circuit. How to actually deal with parallel AC circuit. So before actually getting to the parallel AC circuit and how to solve this actually things, let me actually introduce a new term called is admittance. Do you guys actually familiar with the term called admittance? Have you heard of it before? Probably not.
No, sir.
No, perfect. Thank you. No problem. So admittance is another term, just like impedance. Admittance is the opposite of impedance, like just the inverse of actually. And just the opposite of impedance. So admittance is something like this. Okay. So for admittance, it's a complex number. Admittance is opposite of impedance. Have you heard of conductance? Probably you heard of conductance,
Yes,
right?
sir.
Yes,
So
sir.
conductance is what? The inverse of resistance. So conductance
Yes, sir.
and resistance are the properties of DC circuit, because these are the real number. It's not a complex number. So if I have a resistor and if I take the inverse of it, so that is called conductance. So resistor means the ability to resist the current flow, and conductance means the ability to assist the current flow. So just the opposite things. Means, let's say you have a friend and you have an enemy and you want to do something, your friend will actually support that, right? And or help that, and he will be called as conductance, and who will actually resist your work will be called as resistance. So These two are, just the like opposite, things. So admittance is just the opposite of, impedance. Since impedance is a complex number, admittance is also in a complex number, but these are really actually helpful for parallel circuit, as we'll be actually discussing after a few minutes probably. So in order to define the admittance completely, since it's a complex number, there should be two terms: conductance, which is actually opposite of or inverse of actually resistance. So this is a real number. This is a real number, and susceptance is like there is another term is called susceptance. So susceptance is nothing but the inverse of reactance. So this is the inverse of reactance. If you recall, what we have learned in the last actually two sessions probably, we had been actually saying a lot about reactance. So what types of reactance did we learn? Like two types of reactance, right? One is called actually inductive reactance, and another is called capacitive reactance, like XL equal to omega L and XC equal to 1 upon omega C. This we have learned, right? This is called like inductive actually reactance, and this one is called actually capacitive reactance. Is there any confusion like what we learned from the last class?
No, sir, no problem.
Perfect. So the susceptance is actually denoted by the term B, and conductance is denoted by Z. So Z equal to 1 upon R. B. So B could be in two types. One is called inductive susceptance. So this is nothing but the inverse, the inverse or the reciprocal term of the inductive actually reactance. So this is nothing but 1 upon omega L, and this is nothing but the omega times C. Is there any confusion? So, and remember, this is a purely imaginary number. Purely imaginary number. Why? If you recall in XL and XC, if you recall ZL, it was J omega L, and ZC was minus J times 1 upon omega C. Both ZL and ZL and ZC are purely imaginary number, right? Because it has no real part. Any confusion with this? Hello?
No, sir.
No, sir.
Okay, let me actually see it properly. Okay, if this one is the case, what is the total admittance? So admittance, as I said, is a inverse of actually impedance, and it should be a complex number. So if we know the actually impedance of this, if I take inverse of that, then it will get actually the what is it called, like admittance of the circuit. So just try to find out what would be the like admittance of resistor, capacitor, or inductor first. So we have already learned like what is the impedance of resistor, right? This is R, 0 degree. That we have learned before, right? So
Yes, sir.
if we have learned this before, so then what would be the like admittance of resistor? So 1 upon ZR. So if I do so, I will get 1 upon R, angle is still 0 degree. So 1 upon R is called the conductance. So I will just put in the conductance. Is there any confusion here?
No, sir.
No, you don't need to remember this thing probably, but I just
No,
need to
sir.
actually give you an idea. So similarly, for the inductor, we know inductor ZL means XL 90 degree or omega L 90 degree. So the inverse of that one would be the called the inductive actually admittance. And this is nothing but this. Actually, XL means 1 upon omega L. So BL is nothing but 1 upon XL equal to 1 upon omega times L. Any confusion here? Probably not. If there is not a problem, oh, now check, this angle become negative 90 degree. Can you tell me why? Because
Sir,
we knew from
J equal so minus J equal 1 by J.
yes, perfect. So another thing is like ZL equal to XL 90 degree, right? Plus 90 degree for the impedance. So it was on the denominator, right? What is the angle here? 0 degree. So 1 upon XL, what is the total angle would be here? 0 degree minus 90 degrees. So 0 degree minus 90 degree means negative 90 degree. Be careful with that. Similarly for capacitor, we know that for the capacitor impedance is XA, then angle is minus 90 degrees. So the total admittance should be the inverse of this one, right? So I will just put that value and it would be becoming a plus 90 degree. Do you understand this? Now can you tell me, does it mean the current is leading here? So previously we know current is lagging here, right? Sorry, current is leading. Current is leading. Now, does it mean here current is lagging, or is still current
No.
is leading?
No, sir. Current will be
Still
leading.
it's leading.
It's leading. It's just the notation we are talking about. Okay, like so. What is called the admittance diagram? Same thing of the impedance diagram. Only things like we'll be plotting in admittance instead of actually impedance. So previously we calculated actually impedance and then we plot it in the complex plane depending on the angle. So that was called the impedance diagram. For the admittance diagram, we'll be actually calculating the admittance first of this actually electrical components, and then we'll be plotting. And here are the few basic things: Z times 0 degree for the resistor, BL comma negative 90 degree for inductor, and for the capacitor is BC, then positive 90 degree. And these all are easy. 0 degree means on the real axis, negative 90 degree means this is negative 90 degree, and this is 90 degrees. So all I have to do is just draw this one. And what are the expression of Z is 1 upon R. What is the expression of BL? 1 upon XL, or 1 upon omega times L, and this one is 1 upon XC, or this is nothing but the omega C. Any confusion here?
No problem, sir.
No problem. Let me set this one. All right. If this one is the case, find the admittance of the each set of actually series elements. So if I want to calculate admittance, we know admittance is the opposite of actually impedance, right? Can I calculate impedance of this? What would be the impedance of this? First calculate impedance.
Yes, sir. Just we just have to, plus. Yeah, that's it.
Yeah. Some people may say, oh, why did I use negative? Forget about this. Then draw the impedance diagram. Calculate ZR and calculate ZC. Then use ZR
ZR plus
ZC.
ZC.
Then
Yes,
you will
sir.
get the same value. Okay, don't get actually confused. So once I calculate Z, can I take the inverse using calculator?
Yes,
I
sir.
can do, right? So then I can calculate the admittance here. Similarly here, how would I do that? Can anybody actually give me a hint?
Yes, sir. We
I'll
just
calculate
have
ZR
ZR plus
ZR, ZL, ZC.
ZL
and
and
ZC,
ZC.
and then
Yes, sir.
I will calculate Z equal to ZR
ZR plus ZL plus ZC.
ZL plus ZC. Once I actually get this value, Y would be is nothing but the 1 upon Z. Any
Yes, sir.
idea? Any confusion?
No,
How
sir.
about
Easy.
other students? Are they sleeping, or they have just joined and doing other works? Huh? Or is the noon time is lunchtime probably, right? They might be hungry also. I don't know. Why don't they actually interact? But I suggest to other student, if they are not like okay with, or like comfortable with English, they can actually ask a question or any queries in Bangla. Okay, I would actually prefer Bangla for taking classes, but I am afraid sometimes I cannot actually explain wow properly probably, but you all can actually communicate with me in Bangla if you need, no problem at all. So as I said, we can calculate actually the admittance in the similar fashion. So why would we actually learn the admittance, we have already learned impedance. Actually, there is no need. We can always solve without even actually going for the admittance. But sometimes it's so actually useful, especially for the parallel circuit. Why? Let's have a look. So let's say we had a parallel combination of many actually resistor. What was the actually formula for finding the equivalent resistor? Means the total equivalent resistor. The formula was like this,
Sir,
right?
yes, sir.
1 upon RT is the total actually resistance, is equal to whatever value we have, we'll take the reciprocal of this or the inverse of this and then add up everything, right? Now
Yes, sir, exactly.
if you recall what we learned, 1 upon R means Z, right? The conductance.
Yes, sir.
Yes, sir.
You remember? Then what is
Yes,
that?
sir.
This Z1 plus
Z1 plus Z2 plus
Z2
Z3,
plus
then
then
dot the
Zn, right?
Zn. Yes, sir.
So basically, if we know the conductance of, since it's a parallel circuit, if I know the conductance of the first element, second element, and the nth element, if I add up everything, then we'll get the total actually total actually conductance, right? The similar fashion in the AC circuit, we don't know whether it's a resistor, inductor, or capacitor, or a combination of that. We can calculate the impedance of this, right? So if I have n number of actually branches, that Z could be R, Z could be C, Z could be L, or Z could be RLC or RC or RL or LC. Do you understand? What does it mean? I'll actually explain further. So if I know the impedance of each and every actually branches, we can also calculate then what would be the total impedance formula. 1 upon ZT equal to 1 upon Z1, 1 upon Z2 plus dot 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 1 upon Z1, Zn. Actually, this is enough. We don't need to go for admittance at all. But the only problem is, since Z is a complex number, once we try to actually calculate this, especially in calculator, it will take long time. It will take long time. Sometimes it's this calculations actually really messy, look really messy. So in order to actually avoid this actually problem, what we can do, we can take the advantage of using actually admittance only for the parallel circuit. So for the parallel circuit, we know 1 upon ZT means the total admittance. This is the admittance of the first branch. This is the second branch admittance. This is the nth branch actually admittance. Do you understand what I'm trying to say?
Yes, sir.
Yes, sir.
All right. Now, let's say you have a circuit like this. This is R, this is C. Another branch is, let's say, C, then L, L, and L1, and another one, this is C1. Let's say this is R, and then L, R, R1, C1, C2, L2, are connected like this. Can anybody tell me, is it possible to calculate YT?
Yes, sir.
What is the condition? Generally, it should be a parallel circuit. But you see, are these in parallel? Yes, these are in parallel, but
But
every
also
branch
in series, they've got
in
a
a
series
parallel.
connection.
But can I actually convert this thing into a single Z using series formula?
Yes, sir. Yes,
Yes,
sir.
sir.
R1 plus XC, just like
Yes.
using that.
So can I calculate, the Z for the second actually branch?
Yes, sir. We can do it for the all branches.
Yes,
Yes,
because I
sir.
know the impedance of R, I know the impedance of actually C1, so I can calculate actually the total impedance because these two are in series. So Z1 we can calculate. Similarly for the Z2 and Z3. Now it looks like in a parallel circuit, so I can just take Y1 means Z1. What is the inverse of Z1? Y1. Then this one would be Y2. This one is the Y3, and total Y would be the summation of Y1, Y2, and Y3, like this. Do you get my idea, or I'm just saying something?
Yes, sir. Very easy.
Very
Nothing.
easy. Thank you
Yes,
so
sir.
much.
Yes, sir.
Similarly, for the KCL, we know the KCL for the parallel branches, right? The like entering current is equal to the summation of the exiting current or outgoing current. Sometimes it says or sometimes we say at particular actually node the summation of all currents should be 0. So which one is convenient to you? Like entering current equal to outgoing current, or the summation of actually total current is 0.
Sir, anyone is okay.
Anyone is okay?
Anyone of them is
All
okay.
right, it's okay. So if I, let's say I consider this node. So in this node, we'll consider the entering current is negative, so leaving current is positive. It's not a norm. You can also consider entering current as actually positive and leaving current as negative. There is no harm. Okay, but I prefer entering current as actually negative. So you can choose whatever you want to do. Means whatever you have learned in the DC circuit you can apply here. So the total current would be I entering current, so this is a negative sign. Then I1 is leaving current, so plus I1, and another current is leaving from this node is I2, so I put I2 equal to 0. And but the thing is, the only difference between actually the DC and AC is this one is the vector or complex number. These are the complex number. All right.
So we have to take all of them in phasor format, right?
Yes,
When we are
always.
actually
That's we have learned.
calculating.
Whenever we will apply some KVL or KCL voltage division rule, current division rule, or whatever, your first task is to convert each and every term into phasor. Then your calculation would be so easier.
Yes, sir.
All right.
Yes, sir.
I'll be actually ending our session by by actually discussing the current division rule. Do you understand what is called current division rule? Let's say if I have a parallel branch and there is actually current, means the main current, and since it's a parallel branch, that current will be divided into many actually branches, right? Depending on how many branches are there. Just like a supply current, supply, like what is it called? The water supply. Let's say I have a water supply and then it is dividing into many actually branches or something like this. So what would be the current in this branch? What would be the current in this branch? The formula is again, this is nothing but the sum of z.
The
This is again
impedance.
sum of z, but the rule is the I1 means I1 means the impedance of other things, and I2 means the impedance of other things. Now, this is so easy for actually two parallel branches. Do you know how to get in this formula, or I need to explain?
Sir, we know that.
You know that?
No problem. No
How
problem.
about others? If you don't understand, ask me. I can
Yes, sir, we
actually
know that.
explain. You know that?
Yes, sir, we know that, sir.
Perfect. So then, yeah, I don't need to explain everything. So now tell me, I have Z1, then Z2, and Z3. This is I1, I2, I3. This is I. Can anybody actually tell me what would be the expression for I1, then I2, and I3? It would be a task
Sir,
for you
in
to
this
solve.
case, yes, sir. In this case we have
I1
we can use the
I1 is
perfect formula like I1 equal to 1 by Z1 by 1 by Z1 plus 1 by Z2 plus 1 by Z3, and the whole thing will be multiplied with I.
I think you are
Z1
correct.
is
Say it. I can't hear you. Can you
sir.
actually repeat, please? Maybe my internet connection is unstable.
Should I say it
I1 is
again?
equal to
No. There was another student who wanted to say something.
I1 is
Ahmed, please go on. Go on, bro.
Yeah, please go ahead. No problem. Even if you make actually some mistake,
hello.
there will be no harm.
No, Ahmed was trying to say something.
Yes.
Ahmed,
Please, Ahmed, go ahead. Ahmed, Atif, Abrar, probably.
maybe he's having internet problem. Okay.
It's all right. Then
Okay.
what is this formula, right? And
Yes,
who
sir.
doesn't
So
understand? There's actually current division rule, voltage division rule. You can just apply KCL. For me, I do understand the KVL, voltage division rule, current division rule. But in real life or real exam, I have never used this actually formula. So I always stick into, like KVL and KCL. It's easier for me. But it's up to you. Whatever you find it actually easier, you can actually go for that. All
So
right?
the formula that I have just said, it is correct,
Yes,
right, sir?
correct. Yes, correct.
Yes, thank you, sir.
Correct. So this is it for today. I will finish our session a bit early. I need to actually go somewhere for some family occasion. I'm sorry for that. I will stop my
Yes, sir, no problem, sir.
presentation here. I'll be uploading, the class recording as well as on the annotated lecture in the Google Classroom. Oh, I have another announcement to make. Like, we for every courses we have some student mentor or something, like assigned by university
sir.
or something like this. So
Yes, sir, we
probably we have a student mentor called some meme or something. I forget her full name. She posted, some like practice problem in Google Classroom probably, and she actually emailed me that nobody contracted with her. So if you face any problem or if you need any actually suggestion or help, you may actually contact with her. Okay.
Oh,
It
okay,
will
sir.
be quite useful.
So, sir,
Thank you so
what
much.
did
So it
you
is in the
finish in
Google
class
Classroom,
actually?
Bishwajit was saying something.
Sir, did we finish lecture 5 actually today?
Yeah, we have finished in lecture 5.
No, sorry, sir. Lecture 6 actually. Sorry.
No. We have
Still
not
lecture.
finished lecture 6. No. We have not finished. It's
Okay, so the
it's
exam
halfway.
is going to be on up to lecture 5 actually. The next classes.
I will try to actually keep it up to lecture 5, but I will discuss with another teacher. Tashfin Muhammad, right?
Yes,
Yeah,
sir. So that
I will
means the
discuss with
syllabus
him.
can also change, sir.
I will announce, but if I didn't cover, that will never be assessed in the exam.
Sir, one request, sir. Actually, no matter
Yeah,
what
sure.
the
Go ahead.
syllabus is going to be, actually, please actually announce it at least 1 week before the exam date, sir. It will be
All right.
really like painful for
All
us
right.
if
Yeah.
you.
All right.
Okay, sir.
Yeah, I do understand. Yeah. Thank you so much. Any more question or any suggestion? No?
Any practice
sir.
problems, sir? Actually, practice problems will do tremendously good for us. I mean,
Okay.
sir, or
I'll
else
try to.
a book. Yes,
That
sir.
should be good. Yeah.
Okay, sir.
Yeah, I will suggest a book.
Yes, sir. That would be great.
Yeah, I will suggest a book and maybe some practice problem from that book, which you can
Yes, sir.
practice.
Yes, sir.
Otherwise,
That will be really,
otherwise
really
it will be
Yes, sir.
beneficial
Yes,
really
sir.
for
A
us.
difficult.
book would be very
Yeah,
helpful.
thank you so
Yes, sir.
much. Yeah, sometimes this sort of actually discussion and feedbacks are really useful for both student as well as for the teacher. Any more
Okay,
questions?
sir. No, sir. And sir, can we actually guess that there will be at least lecture till up to lecture 5 in the next classes?
Yes. I will try to keep up to lecture 5.
Okay,
I
sir.
will try.
Okay, sir. But it can be more than actually. It can actually include lecture 6.
I'm not sure. I need to talk to him first.
Okay, sir. Okay, sir. Okay, sir.
Yeah. Any more question? No. If not, we'll finish our session here. Okay. Have a nice day.
Okay,
Thanks
sir.
for
Have a
actually
nice day
joining
too.
again. Yeah.
Yes, sir.
Thank you.
Assalamu alaikum, sir.
Assalamu alaikum, sir.
Walaikum assalam.